Okay. See. All right, so good afternoon to you all. Today we shall be looking at S3 chemistry. The topic is carbon and its compounds. This is a very, very important topic in chemistry. And we need to cover it so that we are prepared for this particular unit in chemistry. Many questions from section A and paper 2, section A come from this topic. So it's very key for us to cover it. Okay. Peter, what do you know about carbon? What do you know about carbon? Anything you know about carbon, you can type it in because I see your audio is not on. You didn't connect your audio. If you can hear me, type anything you know about carbon. Okay, Peter, you're off. Hopefully you'll be back soon. But for those who watch this video later, because I'm recording it, so if you watch it later, let us continue. Carbon is a non-metallic element in group 4 of the periodic table, which with an atomic number of 6 and electronic configuration of 2 to 4. It has valence 4. Okay. Carbon has valence 4. Let us look at the occurrence of carbon. Pure carbon is found in the form of diamond. Okay. Okay, Peter, you're back. So I was just going through some of the key things about carbon. And I've said that it has atomic number 6, electronic configuration 2 to 4, and valence 4. It's sure in its purest form, it is found in diamond, and in pure carbon, it can be found as graphite. If you've not seen graphite before, when you check in most cells, the black thing in the middle, that is graphite. Okay, so remember that. Carbon is a constituent of numerous natural occurring substances such as coal, mineral oils, carbonates, organic matter, and in air as carbon dioxide. Also, our bodies contain a lot of carbon. Okay, so when you think of carbon, you can also think of your body because it contains a lot of carbon. Our bodies are carbon-based. Okay. So remember that. Now, with that being said, let us look at the allotropes of carbon. Allotropes of carbon. Now, you may ask, allotropes of carbon, but what is an allotrope or what is allotropy? So allotropy is the existence of an element in more than one form without change in physical state. So the different forms of that particular element is what we call the allotropes. But allotropy is just the existence of an element in more than one form, okay? If we had, let's say, an individual called Peter and he existed in more than one form, we would say that Peter has allotropy. But that is not possible for human beings. It's only possible for elements like carbon. They exist in various forms, and we shall see these forms in which carbon really exists. So an allotrope is one of two or more distinct forms of an element. Okay. The allotropes of carbon are three. There are only three that we know. We have diamond, graphite, like I had explained to you what graphite is, and amorphous carbon. Amorphous carbon, can also call it charcoal. Okay. So those are the allotropes of carbon. Do you have any questions for me so far? Amira is also here. Amira, you're welcome. We're looking at carbon and its compounds. So we have finished the occurrence and the allotropes of carbon. Let's start looking at them in detail. We can start with graphite. Graphite is black, soft, slippery, and hexagonal crystalline substance. Its atoms are joined by strong covalent bonds. Okay. We say graphite can be found in electric cells. That rod inside the electric cell, if you have opened, not an electric cell, those batteries, if you have opened it before, you'll find a black rod, very, very dark, and it's rod-like, it's like a cylinder. That is an example of graphite. We shall see some of the properties of graphite that makes it very good for electric transmission. But so far, let's start with its structure of graphite. So it has two-dimensional hexagonal layer structure in which each carbon atom is covalently bonded to three other carbons. For example, here, as you can see here in the structure, let's take an example of this carbon. Maybe that wouldn't be a very good example. Let's say this one. So this carbon here is bonded to this one, is also bonded to this one, and is bonded to this one right there. Okay, so each carbon is bonded to three other carbons. If we had continued to draw this structure even here, like this, it would look like that, sort of. So there will be another carbon here, right? So again, this one would have, it will be bonded to that, to this up here, and then to this one here. So each carbon in graphite is bonded to three other carbons. All right, each carbon you look at in the structure of graphite. So that's a way to explain the structure. The other part of the structure, or something important about the structure, is that the remaining electron is delocalized on the whole structure. So remember, carbon, we have said it has a valence of what? Who knows the valence of carbon? I mentioned it. If you know it, you can type it or just unmute and say it. What is the valence of carbon? You can type it in the chat if you know it. What is the valence of carbon? Okay, so we said it has valence of 4, okay? It's even right here. Okay, someone had already typed it. Peter said 12, I think. Not true, we can't have valence 12. We can only have valences up to 7. That's where they end. Okay, so for carbon has valence 4. It exhibits valence 4. This means that carbon can only and only bond with any other 4 atoms, any other 4 atoms. Okay, so it has 4 electrons to bond with other atoms, only 4. But in graphite, this carbon is using only 3, so there is 1 less electron. Remember, 4 minus, when you subtract 4 minus 3, you get 1, right? So we have a balance of 1 electron in carbon that is not bonded to anything else, right? Because each carbon has only bonded to 3 other carbons in the structure, meaning each carbon has a free electron. This electron is so free that it moves around the structure, okay? It's moving around the structure of graphite. We shall see the importance of this electron moving around, okay? Electrons can carry something we call charge. This charge is found in electricity. So this can easily explain why graphite can be able to transmit electricity or current, okay? So it's important to remember this 1 electron, this balanced electron, that the one that is not bonded to anything. That electron is key in determining the function of graphite. The other thing about the structure is that the adjacent layers are joined by weak van der Waals forces of attraction. The weak van der Waals forces of attraction, let me change colors here, are these. So these are layers being joined by the weak van der Waals forces of attraction, okay? So this is like one whole layer, and this one up here is also another layer. They're joined by the weak van der Waals forces. These are the layers here. Okay, and the van der Waals forces are joining them, one layer to another, one layer to another, like that. Okay. The van der Waals forces can break, and adjacent layers can slide relatively to each other. This explains why graphite is soft and slippery. So these van der Waals forces are not that strong. There is even the word weak in their name, weak van der Waals forces of attraction. They're so weak that they can break, all right? Can break, and these layers come closer to one another. This is why graphite is soft and slippery, okay? So that's the structure of graphite. Any question about the structure? What questions do you have about the structure of graphite? Do you have any questions about the structure of graphite? Okay, Peter says no questions. Hopefully, Amira, you concur that you have no questions. But if you have any, please feel free to ask. Hope is also here. Wait, yeah, Hope is also here. I was wondering where Hope was. She's never absent. It is okay, Hope. You came late. That is fine. I should have called you earlier, but I was on my way to where I was going to conduct this lesson from. So, all right. So that is the structure of graphite. And if you have any questions, feel free to ask. Now, after looking at the structure of graphite, let us look at the properties. What are the properties of graphite? So it is a black material which feels greasy on touching. If you've touched that rod that I talked about that is found in batteries, especially the radio batteries, those that they call tiger head and other names. If you open them, there is a rod inside there. If you touch it, it is greasy, it's sort of greasy and slippery. That is how graphite feels like. It is opaque, okay, and shiny, very opaque and shiny. Its density is 2.3 grams per cubic centimeters. It has a hexagonal structure, which we have seen. Okay, we have seen the hexagonal structure right there. It conducts electricity. And I'm going to ask you, why does graphite conduct electricity? I've talked about this while explaining the structure. Let me see who remembers. So type it in. What does graphite have that makes it able to conduct electricity? Type it in the chat box and we see what your answer is. Okay, someone has typed it in. Let me see. Peter says mobile electrons. That is correct. So we talked about the delocalized electrons. To be delocalized means you don't have a permanent place. So for example, to be localized, it means you are there stationed. You can't move. To be delocalized means you can move. Okay. So yes, Hope, you're correct. Yeah, these delocalized electrons, or the mobile electrons, you can call them, are the ones that make graphite capable of transmitting electricity or conducting electricity, because they can move the charge from one point to another. And remember, for electricity to be conducted, you need charge to move from one point to another. And it is electrons that carry that charge. Okay, so these mobile electrons are very, very key in making sure that graphite can conduct electricity. So yeah, that is it. These electrons are able to move freely in order to conduct electric current. I think that is the most important property of graphite. Because we'll look at the uses and see. So the uses of graphite, we have used as a protective coating, iron substances to prevent rusting. So it can be used to prevent rusting because we said it is greasy and it's soft. So they just coat those iron metals with graphite to make sure that rust doesn't occur. Graphite conducts electricity because it contains mobile electrons, which is correct. We have seen that. I've explained about the dry cells, like those things of tiger head and all that. Those dry cells contain graphite. That rod inside there, if you have those batteries, just break them apart. Break them apart, you find graphite in there. Okay. If you have them at home, don't worry about your parents quarreling. Just break them apart. Tell them teacher Solomon will pay. Okay, so that you can see graphite. All right, graphite is soft and slippery because of this property. It is used as a lubricant in dynamos and electric motors. I don't know if you guys have seen a dynamo before. They used to be on bicycles. Those bicycles that used to have lamps or lights. The lights were being powered by a dynamo. And those dynamos have a point on them that rotates. And you know that for something that rotates, we need to reduce the friction. So we lubricate to reduce the friction. Graphite can do a good job in lubrication. Now, the easiest way we use graphite is making pencil leads. If you have a pencil at home, you can look at it. That pencil lead is graphite. Okay, in most cases, it is mixed with clay just to make it a little bit strong and not too soft. Okay, because if it is soft, you can't draw anything or write anything using that pencil. And you know, if you use graphite only, of course, it's going to be very, very soft due to its properties. So it's important to mix it with clay or any other substance that they usually mix them with to make sure that it can write or draw. So those are the uses of graphite. We have seen its properties and uses. We have also seen its structure. Now, do you have any questions before we move on to the next allotrope? Any questions? Okay, if you don't have any questions, we can look at diamond. Diamond is a colorless, transparent, and sparkling crystalline substance. It is the hardest substance known. So diamond is so strong. It is very, very, very strong. It's the hardest substance known to man. So that is an important property of diamond. You shall see how this property is used in the functions of diamond. Okay. Now let's dive into the structure of diamond. Diamond has a tetrahedral structure. What is the meaning of tetra? Tetra. Just the word tetra. What's the meaning of the word tetra? You can type the meaning of the word tetra in the chat box if you know it. Okay, someone has typed it in. Hope says it means 12. Maybe. It's not 12. Tetra means 4. So from tri, you go to tetra. Tri is 3. Tetra is 4. So in the tetrahedral structure, the carbon atom is covalently bonded to 4 other carbons, okay? 4 other carbons. So 4, tetra means 4. So it is easier for you to remember the name of this structure by remembering the number 4, which means tetra. So tetrahedral structure. Each carbon is bonded to 4 other atoms, right? Remember, carbon has valence 4. Now, my question is there a free electron in diamond? Is there a free electron in diamond? Who can tell me? We saw that in graphite, each carbon atom was bonded to 3 other atoms and 1 was remaining. Here we are seeing each carbon atom is bonded to 4 other atoms, right? So is there a free electron in diamond? Yes or no? Is there a free electron in diamond? Let's see, someone has typed here. Peter says no. What do the rest think? Is there a free electron in diamond? Hamira, what do you think?
No.
Okay, good job. Good job, Peter and Hamira. Now, the next question will be for Hope to answer. So Hope, if we don't have a free electron in diamond, can diamond transmit or conduct electricity? Can diamond conduct electricity if we don't have a mobile electron or a free electron in it? Let's see. Okay, Hope said no. Hope you are 100% correct. So diamond has no free electron. Therefore, it cannot conduct electricity. All its electrons, since carbon has valence 4, all its electrons are used in the bonding. Okay, all its electrons are used in the bonding. Okay, good job. All right. So this is said here that all the valence electrons of carbon are used in the formation of covalent bond. Therefore, are localized, meaning they can't move. They are localized. This explains why diamond is a non-conductor, like you guys have said. So it's a non-conductor of heat and electricity. Very, very important. Remember that. It doesn't have free mobile electrons. Diamond has a giant structure in 3 dimensions. The strength of diamond and uniformity of bonding make it very hard and not volatile and resistant to chemical attack. So diamond is not volatile, meaning it cannot just vaporize out of nowhere. It is resistant to chemical attack. If you pour a chemical on diamond, you'll hardly make any change on that diamond. Okay. It is so hard that it can be used to cut other metals, like metals. All right. So in factories that make metals, find that there is a diamond that is just cutting them seriously. That's how hard diamond is. So here is the structure, like we've been mentioning. Each carbon, for example, let's take this carbon. Each carbon is bonded to 4 other carbons. So to that, and here, and then lastly here. That is the tetrahedral structure. 4 other carbons. Each carbon is bonded to 4 other carbons. All the valence electrons are utilized here. All the electrons in carbon are utilized for the bonding. That is very, very important for us to remember. So that's the tetrahedral structure. To compare it with that of graphite, down there I have the graphite structure, which is a hexagonal structure. So this is graphite, this is diamond. You see the difference, huge difference. Okay. For the graphite, it even has layers. Diamond, no layers. So let's see the uses of diamond. Okay. Today we'll only concentrate on the allotropes. So we have one more allotrope to look at, then we'll call it a day. So hang on a little bit. Let's look at the uses. It is used for drilling and cutting hard substances like glass. This is because diamond is very hard. So we can use it for drilling and cutting substances like glass. It's also used in the manufacture of necklaces, earrings, because it has a sparkling appearance, which is caused by a high refractive index. You'll study that in physics if you haven't already. It has a high refractive index. So it can be used for manufacturing of necklaces, rings, and all that. Okay, those who get married, your husbands will propose to you with those diamond rings one day. Okay, so that's one other function. Make rings or that people can use to propose to one another or give each other gifts like earrings and necklaces. They look great because of the high refractive index. So those are the uses of diamond. If you have any, you can always add. Okay, let's look at the last allotrope or form of carbon. Hope you're matchmaking seriously. Okay, let's continue. Amorphous carbon. It is impure carbon. It occurs in the form of animal charcoal, wood, charcoal, soot, coke, coal, etc. So all those that I've mentioned contain amorphous carbon. Okay. Amorphous carbon is found in animal charcoal, wood, charcoal, just normal charcoal, soot, coke. So this one, when you cook, if you've ever cooked in a kitchen where you're using firewood, the soot that forms near the roof, that is soot coke right there. Then we have coal. Coal is mined. It also looks like charcoal, except for it can release a lot of heat. That can even be converted into electricity. So a long time ago, factories, trains, and ships used coal to move, okay? Because could be converted to electricity. It's made up of small crystals of graphite. It's a black and opaque. So that's amorphous carbon. All right. Let's look at the uses of amorphous carbon. It has a good absorption power and is used to purify substances, especially solutions and gases. Impurities in solutions can be removed by boiling the solution with activities or active charcoal and filtering the mixture. I don't know if you have ever been sick or had a stomach upset and then you were given a certain tablet that we call active charcoal. It's black. I used to give it to my dog when he used to get stomach upsets. So charcoal is important in purifying things, okay? And you can use it for also your stomach upsets and all that. If you go to a pharmacy, you can always find them there. Granular amorphous carbon has the ability to absorb gases, especially one of the most known toxic one, okay? So those toxic gases, we can use granular amorphous carbon to absorb them, right? The absorption property finds application in industries, especially in the sugar industry, to remove brown color from sugar and the manufacture of gas masks used in mine and by riot police So especially for animal charcoal, okay? Animal charcoal is the best at really removing the brown color from sugar. Okay, so if they ever ask you what type of amorphous carbon is used in the manufacture of sugar, just know it is animal charcoal. I have seen an objective like that in one of the UNEB papers. So, like I told you at the beginning, section A of paper 1 is mostly these carbon and its compounds. They make so many questions about carbon and its compounds from that. So I wanted you to just remember that. Wood charcoal is prepared by heating wood in absence of air so that it doesn't burn or destructive distillation of wood. It is used as fuel. Okay, this one you have seen, Okocha in the villages there, people cut down trees and make charcoal. The way they make this charcoal is just lighting the wood on fire, then covering the wood to make sure that oxygen doesn't penetrate that much. The burning continues, but without oxygen or without enough oxygen. So charcoal is formed. That wood charcoal is formed. I've already talked about animal charcoal, which is used in making sugar. Okay. So let me first finish this, then you can watch this video. It's used as a fuel because it burns. Now we are looking at coke. Coke is a form of carbon that is used as fuel because it burns to liberate a lot of heat energy. It is used as a reducing agent in extraction of metals like iron, lampblack or soot obtained by burning oils. And it's also used for making printers, ink, and black shoe polish. So most of the shoe polish you use is made up of that. Okay. So next time we shall look at the properties of carbon. Let us look at this video, this woman explaining some of the things I've talked about. And then we can call it a day.
Now we have seen how useful is carbon to us. So this makes us curious to know how carbon is able to do this. But before going ahead in this chapter, let's first revise the earlier concepts which we have studied in our earlier chapter, metals and non-metals. And non-metals regarding covalent and ionic bonding. Now we know that atoms can either share, gain or lose electrons to stable their octet, which means they should have 8 electrons in the last shell. Now the compounds which are formed by gain or loss of electrons are called as electrovalent compounds. But the compounds which are formed by the sharing of electrons are called as covalent compounds. And we are going to see the covalent compounds of carbon in this video. But first, let's draw a clear difference between the covalent bonding and electrovalent bonding by studying them in a difference table. Now we have 3 columns. The first column is properties, the second is covalent bonding, and the third is electrovalent bond. Now the first property which we are going to see is formation or the bonding. The covalent bonding is a form of chemical bonding between two non-metallic atoms which is characterized by the sharing of pairs of electrons between atoms of different elements. The electrovalent bonds are the ionic bonds which are formed by giving and taking of electrons. So you see that the covalent bond is between the non-metals and the electrovalent bond is between metals and non-metals. The second property is melting and boiling point. Now the covalent compounds have low melting and boiling points as they do not have strong force of attraction between the molecules. Now in electrovalent bond, there is a strong force of attraction among the molecules of electrovalent bonds, so they have high melting and boiling points. The third property is that what are the components or the atoms they occur in between. So the covalent bonds are between two nonmetals and the electrovalent bonds are between a metal and a nonmetal. Now let's check the fourth property, which is on the basis of polarity. Since none of the atom involved in the bond loses its electron, therefore there is no polarity in the covalent bonds. The atoms are neither positively nor negatively charged. In the electrovalent bond, the metal loses its electron to non-metal. Therefore, the metal atom becomes positively charged and the non-metal atom becomes negatively charged. That means there is a high polarity. Now let's see the fifth property, which is conduction of electricity. Now the covalent compounds generally do not conduct electricity, whereas the electrovalent compounds conduct electricity in their molten state. So we have seen the clear differences between the covalent bonding and the electrovalent bonding. From all the above discussion, it is very clear that atoms try to achieve the noble gas configuration, which means having 8 electrons in their last shell. Now most of the atoms do it either by gaining of electrons or by losing of electrons. We also know that carbon has an atomic number of 6, which means its electronic configuration will be 2 and 4. Now to become stable, carbon either has to gain 4 electrons or has to lose 4 electrons. But both the conditions are not feasible. Now if carbon gains 4 electrons and become carbon 4 negative anion, then it would be difficult for the nucleus with the 6 protons to hold on the 10 electrons. Now another condition is if the carbon loses 4 electrons and becomes carbon 4 positive cation. But a large amount of energy is required to remove 4 electrons, leaving behind 6 protons in the nucleus, holding on to just 2 electrons. So carbon has another method of sharing of electrons with the carbon atom or atoms of other elements. But not only carbon but other elements like hydrogen, oxygen and nitrogen also form compounds by sharing of electrons. Now these sharing has equal number of electrons from both the atoms so as to achieve a stable electronic configuration. So we can define covalent bonding as mutual sharing of electrons so as to achieve an electronic configuration which stabilizes each of the atom. Since carbon gets 4 electrons by sharing of electrons, it will form 4 covalent bond, which means it has a covalency of 4. Therefore, we can say carbon is tetravalent. So its bonds will be shown by 4 single bonds. Till now, we have seen the bonding in carbon. We are going to see the formation of compounds by carbon and other elements in our next video.
Okay, so that is the bonding in carbon. It is important for us to know it because the bonding in carbon is what causes all these changes that we see, which include also the formation of allotropy or allotropes. And we have looked at our allotropes, we have looked at diamond, I've looked at graphite and amorphous carbon. Okay, so 3 allotropes. So that type of bonding in carbon, carbon having the ability to bond with itself causes all these properties. Okay, so it's important to remember that. Hamira just reminded me that we need to finish gaseous exchange. Yes, next week when we meet, we shall finish up gaseous exchange. That is for biology. Okay. So this is the end of today's lesson, unless you guys have questions for me. The next time we meet for chemistry, we shall be looking at the properties of carbon right here. That's where we shall be going. Okay, you're welcome, Hope. Unless you guys have a question for me, this is it. You're welcome, Peter. Okay, see you soon. See you next week for biology, gaseous exchange. Bye-bye.